Hey there, my name is Gary Sims and this is Gary Explains. Now, Pi Day 2020 is upon us. That's the March 14, 3.14 Pi Day for 2020. And today I want to talk about loops inside of Pi. Now, a few weeks ago, there was a Numberphile video which talked about the loops that you can find inside the digits of Pi. So after the 3 point, you then get, of course, this infinite list of digits which make up Pi, and that's been calculated to billions of decimal places. And you can start to analyze some of those numbers, and if you tie a position to each digit, you can kind of create a looping system. Now, after the video that Tom Crawford did with the people there at Numberphile, I wrote a Python program to analyze some different aspects of the loops inside of Pi, and I sent my results to Tom Crawford, and he told me that what I'd found was some new stuff. Now, he's writing a blog post about that and about some other information he got from some other people, but I thought since it was Pi Day, I thought I'd tell you what I found out about the loops inside of Pi, particularly infinite loops inside of the digits of Pi. So if you want to find out more, please let me explain. Okay, so let's take a look at infinite loops in Pi. First, a quick explainer. Here are the digits of Pi. You're probably familiar with the first few, 1, 4, 1, 5, 9, 2, 6. And then most of us kind of start forgetting after. Here are the first 100 digits. So we can actually give each one of these digits a place in the sequence. So 1 is at position 1, 4 is at position 2, this 1 is at position 3, 5 is at position 4, and so on. We can get to position 11 here, all the way up to 19, 20, 21, 22, 23, and we can keep going all the way through 91, 99, and 100. So there are the first 100 digits inside of Pi. Now, let's pick a number, any number that you like, and I'm going to conveniently choose the number 19 because I know it is an interesting number. So if we look at the number 19 and look at it through the sequence of Pi, the first time it occurs is here. If you look back, there is no occurrences of the number 19. And what we can do is we can work out what position it's at, and we take it from this first square. So where the 1 is, that is its position. So that turns out it's actually position 37. Okay, so this was 11, 21, 31, 32, 33, 34, 35, 36, 37. Okay, now the next thing we do is where does 37 appear in Pi? Well, actually, if we keep going, 7, 1, 6, 9, 3, 9, 9, 3, 7, 3, 7. So if we look there, this is where 37 appears. So the position of 19 is in 37, and 37 appears at position 46. So now the question is, where does 46 appear? Well, if we start at the beginning, 1, 4, 1, 5, if we keep going, 3, 5, 8, 9, 7, 9, 3, 8, 4, 6. So there is 46. So we can see a bit of a sequence building up. 19, 37, 46. And 46 is at position 19. Well, that's interesting because 19 first appears here at 37. So what we've actually got is a loop. 19 is at 37, 37 is at 46, 46 is at 19, and therefore you go round and round and round in a loop. And so here it is showing the diagram of how it goes around inside of a loop. Now you can start anywhere in that loop. If we start at 19, we go 37, 46, 19. But if we start at 37, well, that's a position at 46. 46 is at position 19. 19 is position 37. We end up with the loop again. Because it's a loop, you can start anywhere in a loop. The same with 46. 46, 19, 37, 46. Doesn't matter where you start, you always end up going round and round inside of a loop. Now there are other loops in Pi. In fact, this is the only other loop that I can find at the moment, and it's going to be interesting to see whether others can be found. 40, 70, 96, 180, 3000, I'm not going to read them all the way down to 169, and 169 goes to 40, and then you go back round again. So you can start anywhere in this loop. You can start at 169, you can start at 70, you can start at 96, and you'll just keep going around this same loop. Now, let's pick another number, and I'm going to conveniently pick the number 197 because I know that is also interesting. So, where is the number 197? Well, it's actually here. Now, we were here with 19 earlier. Now we're going to go with 197, and we're kind of in the same place. And that's going to be interesting in a moment. So there we are in location 37. 37 is at location 46, as we've seen previously. 46 is up here. That is in position 19. But now we'll get down to 19, and we're not going back to 197. We've gone to 19. And we know that 19 takes us to 37, 37 to 46, and then we go round. So now we're stuck in a loop without ever getting back to 197. So here's the loop: 197, 37, 46, 19, 37, 46, 19, 37, 46, 19, and you go round and round and you never get back to 197. So if you start at 197, you get stuck in an infinite loop and you can't get out. Now let's pick another number, and I'm going to pick the number 819 because I find that interesting as well. It turns out that 819 is in position 197, and 197 is in position 37, 37, 46, 19, 37, 46, 19, 37, 46, 19, and you're stuck again. So even if you start at 819, which is not like 19, because 19 was at 197 was at position 19, but now we're starting at 819, completely different place, you also get stuck in a loop. And there are other infinite loops, and they have to fold back into one of those two loops that we discussed earlier on, one that's got 3740 in it, or that bigger, longer one. So if we look at this one, 706, 96, 180, and I've underlined 96 because when you go through all this sequence, through 169, 40, 70, we recognize that loop, you end up at 96 again, and you go round. And here's a much, much longer one. What's this starting in? This is 1.4 million. Okay, and you go through all this loop. Eventually you get to 40, and then you keep on going, and then we know this loop, 40, 70, 96. We've seen that before. You end up in 40, and again you're stuck. So you can start in some very big places, 1 million, that number, and you can still end up stuck inside this 40 loop. Now, there are some loops that end in 1. So if we start with the number 21, that's in position 93, which takes us to 14. Now, 14, you might remember that today, talking about Pi Day, 314. Well, of course, 14 is in position 1. Let's have a look at that. There's 14. Look, so if we've got 21, that's in position 93. 93 is in position 14. 14, of course, is in position 1. And what's in position 1? 1. So you end up going round 1 to 1 to 1. So it's terminating on 1. Now, 1's an interesting number because it is in position 1. So 1 is in 1, and you get stuck here. You can't go anywhere else. And there are other examples of this. So if you start with 333, 1698, you go through all this sequence. In the end, 93, 14. 14 is a killer because that takes you to 1, and then you're in infinite loop in 1. Another one, 422, 1839, 9323, 14, 1, and you're stuck again in 1. So there are lots of sequences that terminate in 1 because 1 cannot go anywhere else. Now we're talking about Pi Day 314. Today's date is actually 314-2020 if you put the month first. So the string 314-2020 occurs at position 2124060. And the string appears 28 times in the first 200 million digits. So as well as my Python program I wrote, you can also use that website link there to check out some of your own numbers inside of Pi. Now, why am I saying this? This number here, 314-2020, is in position 2124060. Well, they're actually numbers that the number appears at its location. And they're pretty rare, but they do exist. So there is a sequence for this on that the sequence math sequence website. Self-locating string within pi's, the number n such that the string is in position n. So 1 is there, of course. The next one is 16470. Then you've got 44,899 and so on and so on. This is the current list of known numbers that appear in their actual location in Pi. And this was one of the things that was covered in that original Numberphile video. Now, I did a look at this a bit more. If we ignore 1, we see that 16470, 44899 and 7987384 all have occurrences before their self-locating version. This is interesting. Okay, so 1647 appears in position 1602. So there is a version of 16470 that's not at its self-locating position. It happens before, which means you can never terminate on 16470 because you actually end up going to a different place. You can't terminate like 1. Likewise, 44899 appears at 13714, 15399 and 41604. Before it appears at location 44899. So it cannot terminate like a 1 because you'll get to the earlier version of it when you're doing these loops. And also 798738884 appears at position 4626746. before it appears at its self-locating position of 78873844. So it can't terminate a loop like 1. So 1 has been pretty unique until now. However, 711939213 first appears at 711939213. So hey, it's a self-locating number that first appears at that location. This means it has the potential to terminate a loop. That means numbers like 711939213, because 0 is the next digit there in pi, or 71193921308, and all these numbers I list here will eventually point to 719399213. And just like 1, therefore they'll terminate in that position, because 711939213 is in position 711939213, and therefore it finishes there. Note that 711939213 does not appear again in the first billion digits of pi. I have checked myself. So of course there is scope here for looking in other bigger data sets. Okay, that's it. My name is Gary Sims. This is Gary Explains. I really hope you enjoyed this video. Now, I've got all of my findings along with some much longer lists that I've put them all there on this link here on my GitHub repository if you fancy going to check those out. Other than that, that's it. I'll see you in the next one.